everybody. Just wanted to talk to you a little bit today about the notes for section 7.1 and 7.3 for this week, graphing linear inequalities. And I just want to review real quick. A linear inequality looks a lot like the equation of a line, but instead of an equation, it's got these symbols: less than, greater than, less than or equal to, and greater than or equal to. And I know this was covered in Algebra 1, but let's just make sure we remember the important stuff. Alrighty, so if we have y is less than 1/2 x minus 1, let's just pretend it's a line. And I'm going to ask you the first question: is it in y equals mx plus b form? And the answer is yes, it is. Y is less than blah x minus blah, right? So we are in y equals mx plus b form. So let's just go ahead then and graph it. We can go straight to the graph. So I'm going to go ahead and graph the y-intercept, which is -1, and then I'm going to count the slope up 1/2. I can do that all day long if I want. I don't want. And then we can connect the dots. Now stop yourself, because that's the next question. When you connect the dots, would you expect that we should use a solid, that means unbroken, line, or a dashed or dotted line? CK12 calls them dashed. And the answer is all has to do with what symbol you saw. If you are using less than or greater than, you're going to use a dashed line. It means that the points that are on this line don't actually make the inequality true. They're not solutions. If you ever find yourself using one of these signs, you would use a solid line. So we are going to use a dashed line. Okay, now we have another question. If you remember about these inequalities, they involve some shading. And we either shade above or below. And there's a lot of different ways to teach this. If you're familiar with taking a test point, then you can go ahead and use a test point. You pick a point not on your line, and you see if it works, right? I'm going to pick 0, 0, and you can just plug it in. This is the point where the x value is 0 and the y value is 0. And if we plug in a y of 0 is less than 1/2 the x of 0 minus 1. And we just kind of go through our work here. 0 is less than -1. And that's not true. -1 is to the left of 0, so it's the smaller thing. So this is false. And that means we don't shade where this is. Solutions are either on one side or the other. So if this doesn't work, nothing over here will. And we can shade. I kind of like to do it a bit of a cheater way. This is my y-axis right here, right? And this is my y-intercept. I'm going to put a big old dot right there on the y-intercept so you don't miss it. And this says we should shade where y's are getting smaller. Y's are less than our line. So if you go to your y-intercept, y's get smaller down here, and you know to shade below. I like to do it that way because it's a little quicker. I don't have to plug in points and worry that I'm going to make an arithmetic error, because it happens to everybody. Okay, and then we can kind of do a quick check here. I'm going to ask you some questions. Which points are solutions to this inequality? So I'm going to go ahead and ask you if the point 1, 4 is a solution to the inequality. Go ahead, pause me, take your best guess. Okay, the point 1 from the origin over 1 up 4 is not in the shaded region. So it's not a solution. Okay, let's go for the point 4, -2. And if we look over here, the point 1, 2, 3, 4, -2 is totally in our shaded region under the graph. So that means that is a solution, okay? It will make the statement true. And then the last one, let's go with the point 2, 0. The point 2 over 2 up 0 is right there on the line. And we'll check that out in a minute. So take a little guess on what you think. And I'm going to go back and do this one other way. I'm going to go ahead and look at this point 1, 4. This is my x, this is my y, and I'm actually going to plug it in. I love doing these graphically, but I'm actually going to plug them in right now and show you what they call algebraically by doing the math. This equation, y is 4, is less than 1/2 x minus 1. Oops. And our x value here was 1. So I'm sorry, I'm going to plug in a 1 for x and a 4 for y in this original equation. And I'm going to do some simplifying. 1/2 of 1 is 1/2 minus 1. If I'm at 1/2 and I go left 1, I'm at negative 1/2. And look, 4 is not less than a negative number, so we know this is not a solution. So you could look at it graphically, which I love, or you could look at it algebraically. All right, let's try again. This is my y value is negative 2. So is negative 2 less than 1/2 of our x minus 1? So I'm just plugging my x and my y right in this equation. And I'm going to simplify the right-hand side. 1/2 of 4 is 2. 2 minus 1 is 1. And 1 is actually bigger than a negative number. So we know this is a solution. It made this true. All right, let's try plugging in here. My y value is 0. My x value is 2. And so I'm going to simplify the right side. 1/2 of 2 is 1. 1 minus 1 is 0. Is 0 less than 0? And the answer to that is no. No, it's not. It's like saying you're younger than yourself, right? 0 is not less than itself. So the points that are right on these lines, the dashed lines, are not actually solutions. They're boundaries for the solutions. Okay, let's try another couple, but we'll move through a wee bit faster here, right? Let's see. We'll make all our decisions. If you want to work ahead, pause me and go ahead because I think you can see all the questions there. And I'm going to fold this paper down. You guys give that a shot. Pause me because I'm going to go through pretty quickly. All right. Y mx plus b. This is definitely in the form that's really ready to graph, so we're going to go for it. I'm going to go to 2, and my slope is down 3/1. It does look like the line is going downhill. And then, oops, I better not do that yet. I have to ask myself the all-important question, solid or dashed? And the answer is because we have a greater than or equal sign, either of these two is solid line, I'm going to draw a solid line. What that means is that points on the line are actually solutions. They're going to make the equation true if you were to take the time to plug them in. Alrighty, shading above or below. I'm going to get my y-axis here. And this is my y-intercept. I'm going to look just at that point. And it says I want to shade where y's are bigger. Y's get bigger up, not down. So I'm going to shade up top. Alrighty, and then we'll take a quick look at which points are solutions. I'm going to go with the point. And you can plug these in. Okay, be careful finding these points. All right, the point 1, negative 1, 1 is right here. I'm going to say no, not a solution. And if we were to plug it in, this original one, our y is 1, negative 3 times our x is negative 1, plus 2. I'm getting 1 is greater than or equal to, that's positive 3 plus 2 is 5. 1 is not bigger than 5, okay, nor is it equal to 5. All right, let's look at the next one. Graphically, the point 2, 3 is right here, and that looks like it's in the shaded region, so I'm going to say, yep, that truly is a solution. And if we plug it in the equation, my y is 3, negative 3 times our x, which is 2, plus 2. I'm getting 3 is greater than or equal to negative 6 plus 2 is negative 4, and y is bigger than negative 4. So yeah, it's true. The point 1, negative 1, you knew I was going to do this, is right on this line. So let's go ahead and see if we think it's solutions. I think I recall myself saying that if the line was solid, they actually were solutions. So I'm going to guess yes. But let's prove it by plugging it in. Our y is negative 1. It's greater than or equal to negative 3 times our x. Negative 3 times 1 is negative 3, plus 2 is negative 1. And negative 1 is greater than or equal to itself. It truly is. It is equal to itself. It's like saying you're at least as old as you are. Okay, that's a little complicated. Okay, folks, I got a couple more to try.